So you've watched two videos on aldols already, aldol reactions. This third video is going to have us look at a mixed aldol, having two different carbonyl compounds reacting with each other and see what the consequences are. So propanol and acetone reacting with each other. There's alpha hydrogens on the propanol and alpha hydrogens on the acetone. So if we add our base, then the propanol will be deprotonated in equilibrium. So some of the propanol will be in the enolate form, and some of the acetone will be in the enolate form as well. So now what we have is, in this mixture, we have two nucleophiles, two different enolates, and two electrophiles. So go ahead and pause the video and draw all four products that form. A, this electrophile reacting with, it can react with its enolate, so A to A1 forming, B reacting with B1, and then B reacting with A1, and A reacting with B1. So go ahead and draw those four products that form here. And when you start it up again, then I will show you, I will draw out the products for you, and you can check your work. Okay, so A reacting with itself, we have the propanol. Alpha carbon is double bonded to what used to be the carbonyl of the other molecule. And we have A reacting with A1. If acetone reacts with itself, then we have two acetone molecules stuck together. If we have the B, the acetone, reacting with the A1 enolate, if we're drawing the A1 enolate reacting with acetone, we get that product, and then the acetone enolate reacting with the propanol molecule, we get this. So we get an ugly mixture of four different products. I'll give you I'll give you another one that you can work on your own right now, and then we'll come back to some solutions to these mixtures. Obviously, a reaction that gives you four products is of no use to you. You want a reaction that gives primarily one product that is relatively easy to purify. So this is for work on your own here. We have, again, two different carbonyl compounds. And we're going to have you react it with sodium hydroxide. You can draw the enolates that form, and then draw all the products that form there. So you can do that on your own. I'll post a key for that. But let's go and try to solve our problem that we had up at the top here. Say that we wanted to actually form this as a major product, the enolate from the acetone. So basically we want the acetone, we want an acetone enolate, but we don't want an aldehyde enolate if we wanted to make this. So then the aldehyde would be, this would be the electrophile, and then this would be the nucleophile. So how can we make acetone nucleophile only and have the aldehyde be the electrophile? Well, remember, we have something that is much more acidic than acetone, and that is a equivalent to acetone. Remember acetoacetic ester? This part right here gets delivered. We can blow this off as CO2. And so the great advantage is if we dump this in here together with the aldehyde that we're interested in reacting with it, and we add sodium ethoxide, then what we have is we have much more acidic hydrogens right here, and very little of this is going to be deprotonated compared to here, and this will be completely deprotonated. So in step number 1, then we have converted acetoacetic ester into its enolate, 100% into its enolate. And then step number 2, it's going to react with the aldehyde that we want it to react with. And so what's the product of that reaction? Before we do the decarboxylation, then we have, well, at least initially we have, we're adding to carbon number 1 of our propanol here. So here's carbon number 1, 2, 3. So here's our initial product. And then if we add H3O to it and heat, then we lose a molecule of water here. We convert this to a carboxylic acid and decarboxylate it, and we get the one product that we are interested in with the double bond here and the chain. So this is the AB1 product. Okay, so there are ways to get around the mess that we saw in the first problem. And one way to do that is to start out with one of the two carbonyls having very acidic hydrogens. Then we're forming that's 100% enolate, and then all of the, if we add the base in there, all of the bases can react here, and there'll be no base left to even react with the aldehyde. And so even though potentially this could be an equilibrium with enolate, it's not, because the base is all used up in forming the original enolate. So that's one way to deal with the problem. Specific situations will work if one component has no alpha hydrogens. Okay, so if one of the components has no alpha hydrogens, then it will not be the enolate. It cannot become an enolate, and so then it can it will act as the electrophile, and you can potentially get just one product. So let's look at a couple of examples there. Benzaldehyde, no alpha hydrogens. Here is your alpha carbon, and there are no hydrogens on there, period. So benzaldehyde would be something that you could react in a mixed aldol reaction. Another example would be this aldehyde here. 1,2,3 propanol with 2 methyls on it, 2,2-dimethyl propanol, no alpha hydrogens. And here's a simple aldehyde that you know has no alpha hydrogens, formaldehyde. So if one of the components has one kind of alpha hydrogen and the other component has no alpha hydrogens, then you could do a mixed aldol reaction and get only a single product. So again, the example that I gave you up here is to be worked on your own. Think through how many enolates there are, how many different nucleophiles are there, and how many different electrophiles. So how many combinations are there and how many products, and then you can look for the key posted on Blackboard.